For this lecture, we're going to start by examining, by developing expressions for the eigenvalues for the L squared operator, angular momentum squared, and the LZ operator. And in this case, we're looking at YLM, the spherical harmonics, as an eigenfunction. And I say spherical harmonics, these are also eigenfunctions of the Hamiltonian. So these are the states, the rotational states of the system are represented by these spherical harmonics or YLMs. So we're going to start by observing, we're going to sort of back out, at least in one case here, we're going to back out what the eigenvalues for L squared are by a sort of mathematical argument, not by the sort of direct route. So we're going to go kind of an indirect route. So we could actually take our Lx, Ly, and Lz operators in spherical polar coordinates, square them, add them together to get an L squared operator, and then we could act that operator on our wave functions, and that would be one approach. There's kind of a shortcut that we can take. In that the problem has already been sort of solved in that these are eigenfunctions of the Hamiltonian, and you may recall for classical mechanics, the kinetic energy of a rigid rotor is L squared over 2I, where again, capital I here is the moment of inertia. It's mu r squared, or mass times r squared, where r is the length of the rigid arm in the rotor. And so switching to, if this is true classically, it must also be true quantum mechanically. And we know that there's no potential energy in the system, so the Hamiltonian is equal to the kinetic energy since there's no potential energy term, right? So Hamiltonian is kinetic energy plus potential energy, but if potential energy is zero, then it's just the kinetic energy. So this is true in this instance. It's not always true, right? If the potential is non-zero, then we can't make this statement, okay? But in this case, it's true, and so we can replace the kinetic energy in that expression above with the Hamiltonian, and we can replace the L squared, the classical L squared, with the operator, and that's going to give us Hamiltonian is equal to L squared over 2I, or or in other words, rearranging L squared is equal to 2I times the Hamiltonian. And remember, I is nothing complicated here. It's just mu r squared, and r is fixed. It's constant for this system. It's going to vary from system to system, but if we're sticking within one system at a time, then it's a constant. So we can do a little inspection in that we know that the Schrodinger equation for the rigid rotor in terms of the eigenvalues of the Hamiltonian is written as follows. H YLM is equal to L plus 1 H bar squared YLM, and this is over 2I. Okay, therefore, by comparing this to the expression above, if we just multiply both sides by 2I, we get the 2I cancels on the left-hand side, and we get, and 2IH, where H is the Hamiltonian, is L squared. So if this is true, then this has to be true. L squared acting on the YLM is equal to L times L plus 1. That's little l, or script L, H bar squared YLM. So this is the expression for the eigenvalue of the eigenvalues of L squared acting on the YLM function. And another thing I would like to reiterate here, or remind you, is that little l is the angular momentum quantum number. And so that the cursive, the script L, is that, and it has values 0, 1, 2, dot, dot, dot. It can have any one of those values. So, and different values are going to correspond to different states of the system. So possible states are y00, y10, y11, y1 minus 1, and so on. So now we know we have an expression for the eigenvalue of the L squared operator, and we were able to do this sort of implicitly using what we had previously been told about the Hamiltonian operator, and noting that the Hamiltonian operator is just the L squared operator divided by 2I. Okay, so nothing too terribly fancy here. And of course we can check this by actually acting the L squared operator in terms of the various derivatives, act that on the various spherical harmonic functions, only a few of which we've shown, but we can look up other ones. And there's a like in the case of the Hermite polynomials for the harmonic oscillator, there's a recursion relation. Once you have a couple of the YLMs, you can generate all the other ones from those from the ones that you already have. Yeah, so we have an expression for the eigenvalues of the L squared operator. And again, we haven't proven it here, but we certainly have we haven't proven it rigorously using differential operators. Rather, we've just used what we were already given in terms of the Hamiltonian operator, and just doing a little bit of algebra. But this can be verified. But we're not going to do that here. That would be a great homework problem. Now let's move on to the LZ operator. For this, we take a little bit different approach. The YLM are all of the form that YLM equals some normalization constant times some function of theta. Or you can sort of lump the normalization constant in with the function of theta, either way. And then you have some function of phi which is simply e to the I m phi. So if m is 1, then it's e to the I phi. If m is 0, then it's e to the 0, which is 1. If m is minus 1, then it's e to the minus I phi. If m is 2, it's e to the 2I phi, and so on. Right? So we have to properly instantiate for the given YLM that we're interested in. But this is a general expression which has many instances for different values of L and M, quantum numbers, where M is the magnetic quantum number. And we found above that, or we were given the fact that LZ is of the form, in its differential form, in terms of, in spherical polar coordinates, LZ is minus I h bar d phi. And so then noting that the differential operator only really acts on the parts that contain phi, right? The other parts are just sort of spectators. They get carried along, but they don't matter. They act as constants. And so if we're taking the derivative with respect to phi, it's only going to act on the e to the im phi part. It's going to sort of ignore or pass along the normalization constant and the function of theta part. And and d phi of e to the I m phi is going to give you I m e to the I m phi. And again, I here is the square root of minus 1. That's indicating this is a imaginary argument in the exponential. And so then combining that together, we get that LZ acting on some general YLM is going to be M H bar YLM. And so when we're tasked with some problem involving an expectation value of a YLM, or maybe it's a linear combination of YLMs, you would distribute the LZ operator over that linear combination, or just act it on, if it's not a linear combination, just act it on the YLM in question, and it will give you M H bar. And we'll see later, we'll deal with linear combinations of YLMs because we're going to, sort of peeking ahead here, we're actually going to make linear combinations of YLMs to build up the, say, the various 2p orbitals, the 2px, 2py, 2pz orbitals when we get to the hydrogen atom. But for now, we will use this. We will come back to it. But for now, this is as far as we need to take that. So and let's look at some specific examples. So this sometimes this might seem a little abstract. So let's look at some specific examples. What this implies then is that, say, if we have LZ and we're acting it on y1 comma 1, that's going to give us h bar y1 comma 1. If we act the LZ operator on y1 comma minus 1, then that's going to give us minus h bar y1 comma minus 1. And here's one that seems a little tricky. And so this one's a special case, or kind of an edge case. We know that we have cases where the m quantum number is equal to 0. Also, the L quantum number can be equal to 0. So let's look at y1 comma 0. that is going to give us 0. And this is fine. And the eigenvalue, an eigenvalue of 0 is okay. It might make us pause for a second, but it doesn't mean we just stop. So an eigenvalue of 0 is okay. It just looks like it doesn't quite seem to follow the typical form of operator acting on function, gives you constant times the function. I mean, you can think of the function as still being there, but it's being multiplied by 0, and so you don't see it, right? Anything times 0 is 0, but that's okay. We can have 0 eigenvalues. This is sometimes a question that gets asked on an exam, and yes, it's okay. It's not really. It might cause some concern, but within the machinery of quantum mechanics, it doesn't really gum up the works. We can go on and use this to calculate expectation values, and we get an expectation value of 0, and that's fine, and that jibes with experiment. So experimentally, this seems to work okay. It just means that this is a special case that we have to be a little bit careful with, but it's okay. Now let's see. I think I'm going to skip that. Oh yeah, well no, let's talk about this. Okay, so if we said that our YLM is some normalization constant times f of theta times e to the I m phi. Okay, I sort of, what happens to the n and the f of theta when I act the operator? Okay, so we take minus I. So let's look at this a little bit more detail. So if we take the derivative with respect to phi of this expression, this product of some normalization constant times f of theta times e to the I m phi, what happens? Well, we know that the derivative of a constant times a function is just equal to the constant times the derivative of the function. So the constant is sort of not directly involved, but it doesn't go away either. So we take the derivative of the EIM phi, and then we multiply it by n f of theta e to the IM phi. So that's going to give us minus I h bar, and then we're going to get the n and the f of theta, and then we get the I m and the e to the I m phi. Okay, and then we combine the minus I times I is it's just 1. And we get h bar, and we get m, and we get n f of theta e to the I m phi. Okay, so what's the eigenvalue here? So you're, again, if we look at the definition of eigenvalue, you say, well, okay, so you act an operator on a function, you get back the same function times some collection of constants, and that collection of constants is the eigenvalue. So you might be tempted to say that the eigenvalue is h bar m n f of theta n f of theta, but these are all part of the YLM. So we have to sort of keep track of our grouping here, in that all of this stuff, the n f of theta e to the I m phi, that's YLM, and this is the eigenvalue. Right, so so just be careful when you run across these kinds of problems not to sort of lump the normalization constant in with the eigenvalue. You have to kind of and you may have to do a little bit of math to pull out all of the original functions and sort of separate it into the original functions and constants on the one hand, and then the eigenvalue on the other hand. So there's a little bit of a partitioning there that we have to be careful with. Anyways, I'm not sure if I made my point clearly there, but in this case, the eigenvalue would be h bar m, and it would not include the normalization constant or the f of theta. Those are all part of the YLM. This is just a little bit different than sort of typical everyday algebra, so it's worth perhaps talking about that for a minute. Let's circle back and take a look at commutators of these Lx, Ly, and Lz. Now, I said that the L squared operator commutes with the Lz operator. In other words, its commutator is 0. But that is not true for say, Lx and Ly. So let's take a look at these commutators of Lx and Ly, or Ly and Lz, and so on. And this is a nice exercise in commutators and the associated mathematical steps. So first of all, let's reiterate what our Lx operators are, and we're going to do it just in terms of Cartesian coordinates. Lx equals y pz minus z py. And you notice that these look a little bit like a commutator, but these come right out of the determinant that's used, the determinant form of the cross product, the vector cross product. But they look a little bit like reminiscent of a commutator. You remember that a commutator, if you have two operators A and B, that's going to be AB minus BA. Okay, so here's our Lx, our Ly. Again, you can go back to the the classical version of this, look at the associated determinant, and then plug in the quantum mechanical operators, and you'll get these expressions for Ly that involves rotation in the xz plane, and it's zpx minus xpz and Lz is xpy minus ypx. Okay, and so those are our operators. Now let's try looking at the commutator of Lx and Ly. That's going to be and we might have to bring in a dummy function, but it turns out we probably don't. But we remember for the case of position and momentum, previously we introduced a dummy function, so we might have to do that. But we're going to start off without the dummy function and see if we can solve this without this and without actually having to take the derivative. So if we actually have to take a derivative, then we're going to have to insert a dummy function. All right, so let's go ahead and look at this. So that's going to be, again, according to our definition of a commutator, it's Lx Ly minus Ly Lx. And so then we can plug in our expressions for Lx and Ly in terms of the x, y, z, and px, py, and pz operators. Okay, so that's going to give us y pz minus z py. That's our Lx operator times our Ly operator is zpx minus xpz. Okay, and then that's going to be minus zpx minus x pz, and running out of space here. And then we have the Lx operator, which is ypz minus zpy. Okay, so then we have to do some distributing, some canceling. We have to be careful that we don't accidentally, when we're rearranging things, we can swap, say, an x and a z operator. We can rearrange, we can do some kinds of rearrangements, but other kinds of rearrangements we can't do. Yeah, in other words, we can do a rearrangement when we know that two operators commute. And we have to try to find some other way of handling operators that don't commute, as we'll see. Okay, so then let's multiply these out using FOIL. that's going to give us 8 terms. And 8 terms, and each term is going to have some combination of 4 operators in it. So this gets a little messy. So we're going to get ypz, zpx. So that's from multiplying ypz times zpx. So that's the first in our FOIL. And the outer is going to be minus, or let's do, okay, let's do outer. Outer is going to be ypz zpx. Wait, let's see, outer ypz xpz, sorry. And then inner is going to be minus zpy zpx, and last is going to be plus zpy xpz. Okay, and I'm dropping the hats for now because it's getting a little busy. Okay, so so that's for the first, that's for Lx times Ly. Now let's subtract Ly times Lx. So that's going to give us Ly times Lx. So we're going to get zpx ypz, and we have a minus sign. Oops, we have a minus sign there. So zpx ypz, and let's see, outer is going to be zpx zpy, and we have a minus sign and a minus sign, so those cancel. So that's going to be plus zpx zpy. And then inner is going to give us, again, a plus xpz ypz. And then last is going to give us minus xpz zpy. Okay, now we have to see what we can cancel. So first let's look at this and this. They look very similar. And again, oh, and this one has a minus sign in front. Okay. They have z and y and px and pz. Okay. And they have opposite signs. And if you notice, all of these let's see, so oh yeah, so this looks like actually we can rewrite these two terms here as, let's see, if we can factor out the parts that do commute and the parts that don't. So z and pz do not commute. And but y and px do. So we can factor out the y and the px, and we notice that after we factor out the y and the px, then we get pzz minus zpz, which is the commutator of pz and z. Okay, so that's a little bit simplified. So that's, we've simplified a little bit, maybe. We'll see if there's a way to use that later. And so it's not 100% clear that this approach will work. Okay, then for the foil part, or for the outer and inner parts here, we can group this and this one together. Okay, and let's for ZPY, ZPX. So we have Z, we have two factors of Z, and the Z's commute with themselves. PX and PY commute with Z. And so these cancel. So this is going to give us 0. Similarly, let's take a look at these two. These, again, all have operators that commute with each other. PZ commutes with itself, X and Y commute with each other, and X and Y commute with PZ, so they all commute. So we can rearrange them so that they're exactly the same, and except they have opposite signs, so they're going to add up to 0. And then for the final part, we look at these two terms. So the trick here is we've got 8 different terms here, and you have to find which ones kind of to combine. And here we end up with, we can factor out an x and a py, and then we end up with, when we factor that out, we have z, pz minus pzz, which is the commutator of z and pz. Okay. And what else do we know? We know that the commutator of pz and z is minus I h bar, and this would be plus I h bar, and so we get I h bar xpy minus ypx. And this should look familiar. This is LZ. So we've shown that the commutator of Lx and Ly is I h bar Lz. So there's this nifty relationship this nice relationship between the commutators of Lx and Ly, and we've done the math on this. And so you might be asked on a homework to try some other pair of this triple, maybe commuting Lx with Lz, or Lz with Lx, or Ly with Lz, and you should be able to work through and see you get some kind of similar relationship, maybe with a different sign. Okay, so we've worked through that derivation. So that was just kind of a little bit of a side note, because there may be some homework problems or test problems related to that, and it might not be clear how to proceed unless you've seen how that kind of problem works. Now let's move on to uncertainty in the rigid rotor. All right, what's the orientation of these molecules? Is there some, do we know anything about the orientation? Do we know anything about the angles? And so we're going to look at a few angular momentum states, a few of these, and of course these are, these rigid rotor states are angular momentum states. They're states with some defined angular momentum as given by the L squared operators and LZ operators, and we'll consider sort of what the expectation values are for L squared and LZ, and what that tells us about the sort of direction of rotation or the orientation of these dipoles. And we're also going to compare to the classical case. So first of all, what's our lowest energy angular momentum state? That is the y00 state, and it is a constant. Right? It's just some sort of constant, so that when we do the so that it's normalized, and when you do the normalization integral in spherical polar coordinates, it works out, and it's so something like 1 over square root of 4 pi or something like that. And the acting the Hamiltonian on y00 is 0. So the energy is 0. And again, that's fine. You can have, in some cases, an energy of 0. This happens to be one of those cases. So unlike the particle in a box, where there's a 0-point energy, there is no 0-point energy. So we can think of that as it's a little bit like the case of a particle in an infinite box, where the minimum energy is 0 in that case. In this case, we don't have an infinite box, but it's sort of infinite in that it's sort of circular or spherical, and you can just kind of, you can't point to a place where there's a boundary. I mean, you can sort of say, well, there are limits of integration, in that theta goes from, I believe, 0 and 2 pi, and phi goes between 0 and pi, or it could be the other way around. But in any case, those are just limits of integration. Those are not telling us where the wave function ends. The wave function is actually continuous, and there's essentially no confinement, at least as far as this. It's sort of like if you have a particle in an infinite plane, it doesn't worry, it doesn't, the confinement to that plane isn't a real confinement. It doesn't show up as an energy. It's free within the plane, and that's what matters to its energy, because that's it's only motion in that plane that contributes to the kinetic energy. So in that case, in this case, our quantum mechanical system has a minimum energy that's the same as the minimum energy of a classic rigid rotor. A classic rigid rotor would be, the rotor is at rest, right? There's no rotation going on. That's the minimum energy, and it would have a kinetic energy of 0. So in this case, so whereas in the case of, say, the particle in a box, or in the harmonic oscillator, there was some 0-point energy or some confinement energy. In this case, there is none. And however, there is a difference in that the orientation, essentially for a quantum mechanical rigid rotor, or rigid rotator, the y00 is a constant, meaning that it doesn't depend on the angle. So the probability density is independent of angle. Therefore, there's no real orientation. So instead of having a rigid rotor, we essentially have this probability sphere, this uniform sphere of probability density in spherical polar coordinates, and there's no orientation, and this is akin to, and in fact is related to the fact that s orbitals in the hydrogen atom are spherical. So that's for the y00 state. Let's look at the y11 state. We act L squared on y11. That's going to be L, of course we have to be careful here, L times L plus 1, h bar squared, y11, but then we have to actually instantiate. We have to actually put the value of L into the expression. And we can't just leave it as lowercase l. That would be, you would have an incomplete, unfinished expression. So we have to, so it's going to be equal to 1 times 1 plus 1 h bar squared y11. And we have to actually put the L value into the expression, the little l, the cursive L, and that's going to give us this. Then of course we can simplify, that is then 2h bar squared y1 1. And then it can be easily shown if that is the, remember, if we have a function that's an eigenfunction of an operator, the expectation value is the eigenvalue. And similarly, if we looked at LZ for this, we have to instantiate. We have to actually put the value of m for that YLM into our expression, and then this is going to give us h bar y11. And so our eigenvalue is h bar, and our expectation value is h bar. And our expectation value for LZ squared is just going to be h bar squared. Interesting. So if we compare these, we might notice that, okay, our L squared is 2h bar squared, and our LZ squared is h bar squared. So what does this tell us? Well, so we can say L squared is greater than LZ squared. In fact, it's always greater than LZ squared. And that's because m always has to have a value that's the absolute value of m has to be less than or equal to L. And then our expressions for the eigenvalues give us that L squared is always going to be greater than LZ squared. So this tells us something about the direction of rotation in this system, in that we have some rotation in the xy plane, giving us some angular momentum oriented along the z-axis, but not all of the angular momentum is due to rotation in the xy plane. There's always got to be some extra angular momentum. So therefore, our spinning molecule is spinning it has sort of multiple axes but we don't know exactly what those axes are. We know that there's some angular momentum associated with LZ. There's some uncertainty associated with the directionality of the rotation, and so we don't know exactly which way it's pointing. And it's like the molecule is wobbling and spinning. Sort of got multiple axes of rotation, kind of like say a coin that's spinning and wobbling at the same time. Again, a little bit tricky to visualize, but well, we made a bit of an attempt there. And of course, we just did this for y11, but this is also true for y22 and all of the spherical harmonics. Now, if you say like y55, most of the rotation would be in the xy plane, but there would still be a little bit of wobble left. There'd be sort of 1 quantum of wobble still, even though there's 5 quanta of angular momentum in the along the z-axis associated with rotation along the xy plane, in the xy plane. All right, and that is the end of this lecture. Next lecture, we'll actually switch to rotational spectroscopy.